The North and South Poles are both remote, frozen, and hostile. So why has one become an aviation shortcut, while the other remains almost empty? It's not because flying over Antarctica is illegal. It isn't. Modern jets don't stop working in the cold, and navigation at the bottom of the world works just fine. So what's actually different? It starts with the map. The flat projections we all grew up with distort the real shape of the shortest path between cities. Measured on a globe, the Arctic sits directly between the busiest aviation markets on Earth: North America, Europe, and Asia. Antarctica connects almost nothing, but geometry alone doesn't explain it. Airlines don't build routes for the perfect day. They plan for the engine that fails, the cabin that depressurizes, the passenger who collapses at 40,000 feet. Over the Arctic, a handful of remote but usable airports can absorb that crisis. Over Antarctica's interior, those options approach non-existent. And here's what most people miss. Even if you do put an airliner down safely on Antarctic ground, that landing may only be the beginning of the emergency. To find the shortest path between 2 points on a curved surface, you cannot rely on a flat map. Standard flat maps use projections that stretch the high latitudes, making the top and bottom of the globe appear vastly larger than they are. In reality, the shortest distance between 2 points on a sphere is a geodesic, known in aviation as a great circle route. When projected onto a flat map, these direct paths warp into dramatic, counterintuitive curves that look like massive detours. For airline route planners and dispatchers who analyze the globe as an efficiency problem, these curves are the key to optimizing long-haul flights. High-latitude tracks that appear to go far out of the way on a standard flat screen are actually the straightest lines possible. Major global connections like New York to Tokyo, London to Tokyo, and Los Angeles to Hong Kong regularly arc far into the northern skies, skimming the edges of the Arctic Circle. By following these great circle paths, airlines bypass thousands of miles of unnecessary flight, shaving hours off flight times and reducing fuel consumption by thousands of kilograms per trip. However, flying a northern polar route does not mean crossing the geographic North Pole itself. Aviation regulators divide the extreme north into distinct polar operating zones, and many daily flights only graze the outer boundaries of these regions. The actual track selected for a flight is a dynamic compromise, recalculated for every departure based on seasonal jet streams, shifting high-altitude winds, and geopolitical airspace restrictions. But the underlying mathematics do not change. The Arctic is not a detour, it is the shortest path. This geometric reality aligns the world's major population centers, making the northern skies some of the most heavily traveled corridors in global aviation. While the geometry of a sphere dictates that the shortest path between the northern hemisphere's economic powerhouses lies through the high north, the southern hemisphere presents an entirely different map. An airline dispatcher does not merely look for the shortest line. They must find routes that connect major populations. The world's primary cities and financial hubs are heavily concentrated north of the equator. This distribution of humanity creates a natural bridge across the Arctic, linking North America, Western Europe, and East Asia. In contrast, the major metropolitan hubs of the Southern Hemisphere, such as Sydney, Buenos Aires, and Johannesburg, are separated by vast, open oceans. While flights between these southern cities occasionally skirt the high southern latitudes to catch favorable winds, these tracks merely brush the cold edges of the southern oceans. They do not cross the frozen continent itself. To do so would actually add unnecessary miles to almost any practical route. There is simply no commercial market that requires a flight path directly over the South Pole. Yet this lack of traffic is not just a matter of market geography or empty flight paths. If airliners can cross Arctic wilderness, why is Antarctic wilderness different? The answer appears the moment something goes wrong. The Arctic is remote. Antarctica is isolated. To manage this isolation, international aviation relies on a strict safety framework known as ETOPS, or Extended Range Twin Engine Operational Performance Standards. This regulation dictates exactly how far a twin-engine airliner can fly from an adequate diversion airport, measured in minutes of flying time on a single engine. While modern turbofans are incredibly reliable, dispatchers do not plan for a perfect flight. Airline dispatch is entirely built around abnormal day planning rather than normal cruise performance. Before an aircraft ever pushes back from the gate, a coordinated team of maintenance planners, dispatchers, and flight crews operates as a single chain to map out contingency plans for mid-flight emergencies. They calculate precise diversion paths to account for sudden cabin depressurization, engine failures, onboard smoke warnings, electrical system failures, passenger medical emergencies, or the sudden closure of the destination airport due to severe weather. Every segment of the flight must be covered by a certified diversion window. If a route takes an aircraft outside its approved diversion time from a usable runway, the flight plan cannot be released. This shifts the routing equation from simple geographic efficiency to a rigorous calculation of safety margins, ensuring that if an emergency occurs over the cold wilderness, a safe runway is always within reach. A runway on a map is not automatically usable. For an airline dispatcher, a true diversion alternate must satisfy a strict checklist of real-world capabilities. It requires sufficient runway length and pavement strength to support a fully loaded wide-body jet. It needs round-the-clock rescue and fire services, reliable navigation aids, and the logistical capacity to deplane, shelter, and sustain hundreds of stranded passengers in sub-zero conditions. Shifting winter weather, runway ice, and sudden geopolitical airspace restrictions mean that an airport's availability can change from hour to hour. The Arctic is ringed by a reliable network of these high-latitude safety nets. Active alternates like Anchorage in Alaska, Iqaluit in northern Canada, Keflavik in Iceland, Gander, and well-equipped facilities across northern Norway and Russia provide a continuous shield of operational support. These are not merely emergency landing strips. They are active commercial hubs with heated hangars, heavy ground handling equipment, and established medical infrastructure. This strong northern ring ensures that if an aircraft must descend into the cold, a fully prepared recovery option is always within safe flying distance. The airfields of the far south present a completely different operational reality. Antarctica does have runways, such as the compacted snow of Phoenix Airfield near McMurdo Station, the short gravel strip at Rothera, or the blue ice of Union Glacier. These runways consist of seasonal, non-standard surfaces, offering no wide-body fuel, maintenance facilities, or heavy medical support. These specialized outposts are built to support scientific research, military logistics, and highly targeted expeditions. They operate on a seasonal basis, often shutting down during the dark polar winter, and are not equipped to function as standard commercial alternates. A commercial airliner landing here would find no heated passenger terminals, no fleet of heavy wide-body towing tugs, and no compatible refueling infrastructure. The ground handlers, logistics teams, and rescue coordinators at these remote bases are staffed and supplied to manage small, scientific cohorts, not hundreds of stranded civilians. In this environment, a successful landing is only the first step of a major logistics challenge. Once on the ground, there is no local capacity to shelter passengers or perform aircraft repairs. Preparing a secondary transport aircraft to retrieve a full plane load of people from a remote ice shelf would take days, demanding a massive, coordinated international rescue effort across thousands of miles of empty ocean. Over the Arctic, emergency options are limited. Over Antarctica's interior, they can approach non-existent. When an aircraft touches down on the southern ice, the immediate airborne emergency ends, but a ground-level crisis begins. Antarctica's environmental reality is defined by brutal temperatures, sudden whiteouts, and unrelenting winds that can sweep across an exposed airframe at over 80 miles per hour. During the polar winter, absolute darkness blankets the continent for months, severing the stranded cabin from any visual reference. The tires rest on a shifting, frozen surface thousands of miles from standard civilian support. In this environment, a successful landing merely trades one survival clock for another. A wide-body airliner carries hundreds of passengers, yet the interior of an aircraft rapidly cold soaks once the engines shut down. Within hours, The cabin temperature drops to match the freezing exterior. The location lacks heated passenger terminals, terminal power connections, and emergency facilities to shelter families. The aircraft itself becomes a metal freezer. Sustaining hundreds of people on the ice requires an immediate, massive influx of food, shelter, and medical supplies. Yet local communication networks are sparse, relying on variable satellite links that can degrade in high-latitude storms. Regional rescue capacity is built for small scientific teams, not hundreds of commercial travelers. The nearest heavy transport aircraft capable of staging an evacuation may be days away, waiting for a break in the unpredictable polar weather. A rescue mission must cross thousands of miles of open ocean just to reach the site. The Arctic is remote. Antarctica is isolated. On the southern continent, a safe landing is only the first step. Subscribe to follow more stories of global aviation. A modern jet may be capable of crossing Antarctica on a normal day. Airline rules are built around the abnormal day. Even if an aircraft easily tolerates extreme high-altitude cold during cruise, the real operational bottlenecks begin the moment it touches down. On the ground, fuel temperature monitoring and cold soak constraints become major operational challenges as jet fuel cools toward its freezing point in the wing tanks. On the windswept ice, the simple mechanics of ground handling turn into survival challenges. Standard wide-body airliners require highly specialized heavy equipment for towing, refueling, and basic inspections, assets that are entirely absent from seasonal research outposts. Unlike established Arctic hubs where ground crews can quickly apply heated fuel or move an aircraft into a climate-controlled hangar, Antarctic outposts offer no compatible refueling infrastructure or heated maintenance facilities. This operational divide does not stem from outdated navigation tools. A persistent myth suggests that shifting magnetic fields prevent aircraft from flying near the poles. In reality, modern commercial jets fly through these high latitudes with high precision, completely bypassing magnetic compass limitations by using ring laser gyro inertial reference systems and satellite GPS under specialized polar steering procedures, which automatically transition the flight displays from magnetic to true heading. Similarly, while major advances in satellite and high-frequency radio networks now ensure constant communication over the South Pole, these links only serve to coordinate an emergency response. They do not build heated shelters, melt runway ice, or supply medical infrastructure. For airline dispatchers, the primary barrier remains the absolute lack of physical, ground-level support. Without a dependable network of warm-use alternate airports, the technical capability of the aircraft is secondary to the stark realities of passenger survival. Behind every flight path lies a network planner and a dispatcher, acting as risk managers and economists. Choosing a route is a repeatable business calculation, where a straight line on a globe is only one variable in a complex equation. Dispatchers must balance physical distance against high-altitude winds that shift fuel burn and weigh weather patterns against airspace access fees. They calculate passenger demand against payload limits, making sure cargo weight does not force an expensive refueling stop. At the same time, they factor in crew duty limits, regulatory restrictions, and the potential disruption costs of a diversion. In this quiet math, efficiency is balanced against safety, turning every flight into a carefully calculated decision. When dispatchers run the numbers for the far south, the mathematical benefit of a straight line quickly dissolves. To satisfy strict safety regulations over empty oceans, airlines face severe penalties. Flights must restrict passenger payloads to carry extra fuel, invest in specialized survival equipment, and fund extensive polar training for flight crews. Often, the mandatory flight paths required to stay within safe flying distance of a usable runway end up adding more miles than they save. Ultimately, the cost of mitigating these risks outweighs any theoretical shortcut. The Arctic shortcut connects major markets and can save fuel while remaining within reach of usable airports. An Antarctic crossing usually adds risk without enough economic value. One pole is on the way, the other usually is not. Rigorous engineering and system building transform the Arctic from an impassable barrier into a daily transit corridor. During the late 20th century, the arrival of reliable twin-engine wide-bodies, combined with satellite navigation, solved the tracking hazards of the far north. Better meteorological forecasting and satellite communication networks connected dispatchers directly to flight crews. Regulators supported these technical leaps with expanded ETOPS approvals, securing a chain of active northern alternates. Specialized dispatch procedures, route-specific survival equipment, and passenger recovery plans completed the safety net. The Arctic remains a hostile environment, but aviation built a layered system to manage the risk. Subscribe to follow more stories of global aviation. Flights do cross and land in Antarctica. Scientific research, military logistics, cargo operations, private charters, and seasonal sightseeing flights operate here regularly. Yet these are highly specialized missions, reliant on purpose-built aircraft, expert crews, and strict seasonal windows, rather than routine commercial schedules. In the coming years, advanced satellite tracking, improved weather forecasting, and better remote monitoring will continue to reduce operational friction. However, the southern continent still lacks the year-round diversion airports, robust rescue coverage, and steady passenger demand necessary for scheduled airline routes. The technological barrier is shrinking. The geographic and economic barriers remain. Subscribe to follow more stories of global aviation. Every polar flight is a calculated balance of geometry and emergency planning. While modern jets can physically cross any horizon, commercial aviation always designs for the worst-case scenario. The Arctic is remote. Antarctica is isolated. Ultimately, the shortest path only makes sense when there is a safe way down. Subscribe for more deep dives into aviation engineering.